At this point, it's important that you're sure you know how to represent the front and top views of three-dimensional objects. Take, for instance, a cylinder. Something that looks like this. So let's say this is a cylinder. This is my rough sketch of cylinder. What is your view when you look at, so this is a 3D object, right? What is your view when you look at a cylinder from the top? What's the top view? Your top view is a circle. What you see is a circle. So this is just my rough sketch of a circle. What you see is a circle. You see a circle when you look from the top. All you see is this. That's all you see. You just see this region. What is your side view? So if you're looking from the side. So I think a better way to help you is to draw the cylinder like this. What is your side view? Your side view, when you look from the side, or rather your front view, so front or side view doesn't matter. If you're looking at this side from, let's say you're looking straight at this region, what do you see? What you see is a rectangle. You don't see the curved edges. You see a straight line for this curved edge, and then for this straight side, you just see them as straight lines. This side is simply this, and this curved end here is a straight line. That's what you see. So that's a cylinder. So this is the front top view, and this is the front view. Top view is a circle, and the front view is a rectangle. What about a sphere? Now, it's hard to draw a sphere because a sphere is easier to represent when you shade and you show gradient. But imagine this is a sphere. Imagine this is a sphere. I guess what I'll do is I'll just draw dotted lines just to show that it's a 3D. Maybe this will help to bring out the 3D, three-dimensional element of what I'm drawing. So ignore these dotted lines and just consider this shape as a sphere. What do you see from your front view? If you're just looking from the front, what you see is a circle. What you just see is the outer boundary, and it's just literally a circle. You wouldn't see the protruding portion of this side. All you see is a circle. So what you should do is just get a sphere and try it out at home. Also, from the top view and from any side, you also see a circle. So I'll just skip the sphere. The sphere is really easy. All you see is a circle. What about the top and front view of a hemisphere? So I'll just draw a sketch of a hemisphere. So that's half a sphere. So it's like you got a sphere and you cut it in two halves, and this is the top surface. What do you see? And pay attention here, because the cross sections of hemispheres are going to be very useful when dealing with questions involving latitude and longitude. Now, the top view is simply a circle. All you see is this circle here. So what you literally see is a circle. Your front view, so when you look from the front, what do you see? What do you see? You see half a circle. You see a semicircle. This curvature here, which you can see in 3D, is a straight line in one dimension. What else? So imagine I cut, so I take a point, I'll just draw another hemisphere, so just move. So this is a hemisphere, and this is a point A on this top surface, and this is a point B also on that top surface, and this is the center of the circle, where the circle is this top surface, right? And imagine I form this sector OAB. If you look from the top, what do you see? You see a sector. This is what you see, a sector. You also see the curvature because you're looking from the top, so you will see this curvature. And it's very important because what we're going to be doing in subsequent videos is forming sectors and finding the length of arcs and the angles formed at the center and all sorts of other things. And this being able to deduce the top view of, well, this sector formed here will be useful, or will help you understand how some diagrams are formed in example questions we're going to deal with later. So the key thing here is I formed a sector here on this cross section. If I look from the top, I see a sector. Simple stuff. So now we're going to focus on forming sectors. You find it very useful, but let's just focus on points that are on meridians, on lines of constant longitude. So, of course, longitudes run from the North Pole to the South Pole. So consider this line of longitude. And consider point A here and point B here. And consider the center of the sphere. So this is within the sphere. Point A and B are on the surface, but this point here, we're going to call this point O, is at the center. I think it'd be easier to see if I draw the equator. So point O is at the center. You really need to use your imagination in this topic, latitudes and longitudes. Now, if I draw a line from the center, so within the sphere, to this surface, to this point on the surface, point A, and I also draw another line from center to the surface, point A, what I've just formed is a sector, and that sector is sector OAB. And I'll just shade it. Well, let's consider another line of longitude. So let's say this is the North Pole. This is the South Pole. This is the center of the Earth, which I'll call point O. And I have a line of longitude. I'll show that in white. Let's say this is longitude, who knows, 50 degrees to the east of the prime meridian. So the prime meridian is probably somewhere here. I'm going to locate another point A here and a point B here. Now a sector can be formed by joining the center to point A and also to point B. And I have a sector here, sector OAB as well. So instead of putting O here, I'm going to put O here and shade the sector. So I have a sector here. So I can do the same thing here. I have another line of longitude. So this is another line of longitude, North Pole, South Pole. Another point A, point B. Say the center is somewhere here. Where O. A sector can be formed by joining point O to A and point B. Point A and B lie on the surface of the sphere. So this might not look much of a sector, so I'll try. I mean, you really need to imagine that this side is curved. So something like this. So this kind of sector we formed there with this point O, and that's point A, and that's point B. You're going to find these sectors useful when you're trying to determine latitudes. So yeah, you also use to determine the length of arcs. So let's say you want to find the distance between A and B, you want to form a sector. So let's focus on lines of constant latitude, parallels. So let's see, say the equator is somewhere in the middle here. Well, let's say that's the equator here, there. And this is just randomly chosen line of latitude, a random parallel. You can have a point A that lies on this line of latitude, another point B that lies on the same line of latitude. Now, imagine if you cut through this line of latitude, you'd have a cross section where this is what you have. This is what you have. You have something like this. Going to be something like this, because you're cutting at the top of the sphere. So you have something like this. Point A will be here, point B will be here. So you have something like this, And the center of this top circle is some point O. I'm going to call that point O. And that's what I'm representing here. You can form a sector by joining point O to point A and point O to point B. And if you're looking from the top, so you also have that sector sort of formed here. This is a bit small, but if you're looking from the top, what do you see? You see a sector. It looks like this. O, A, B. There's an angle formed at the center. Who knows what that angle is? Let's try another line of latitude. There's just another one. There's a point here. Call this point point C. Call this point point D. And imagine you cut through the plane of this line of latitude. You'll have this as the cross section, and there'll be a center, and the cross section is a circle, and you form a sector by joining point O to point C and point O to point D. I'm going to put point D here and the center here. So I've just formed a sector. So that's point O and the center. And from, let's say you are looking from below, imagine you cut, let's see. So here's our sphere. So point C somewhere here, point D somewhere here, the center of the circle is here. If you're looking from below, what do you see? You see this cross section. See it? So this I shade this region as the top cross section. It's a circle, and what you see is that there's a point at the center. You see your point. We'll see point C somewhere here, point D somewhere here, and a sector can be formed by joining point O to C and point O to D, and that's the sector here. And there's some angle formed at the center there, and this CD, this line CD, is an arc, and we've dealt with arcs. So I have a sector here. Another thing I'd like to point out is the following. Imagine I just draw two meridians. So this is just some meridian, and this is another line of longitude, another meridian. So say the North Pole is here, South Pole is here. This is a meridian, and this is another one, another line of longitude. Now if I just locate this parallel, and then the equator somewhere here, which is another line of latitude. So this is a line of latitude, and right, there's another one, the equator, and this is another one below. And that's the center of this. Well, if you had a plane cutting through this small circle, this line of latitude, this would be the center. This is the center of the Earth, center of the equator, and this is the center of this circle, this line of latitude, this circular line of latitude. Now, the line from the North Pole passing through all these points will be a vertical line. And one thing I'll stress is, imagine I locate a point. So we have two meridians, two lines of longitude. Now, let's focus on this first line. It intersects with the first latitude at a point I'll call A1. Intersects with the second line of latitude, the equator, at a point I'll call A2. Intersects with the third one at a point I'll call A3. I'll do the same here for the second meridian. Intersects with the first line of latitude, the topmost one, at a point I'll call B1. It intersects, well, it's hard to see here, but intersects on this side with the second line of latitude at a point I'll call B2. So ignore that intersection, because this end of the red line is on the other side. Anyway, this meridian also intersects with the line of latitude here at a point I'll call B3. So this is the center of this small circle, this is the center of this small circle, and that's the center of the Earth, the center of the equator. Sectors can be formed, as you can see. And all I just want to stress, and something you should keep in mind, is the angle formed in each of these sectors is the same. So the central angles of the sectors formed between the same meridians are equal. Same meridians are these black lines, and these are sectors that are formed between these meridians. The central angles are the same. Just keep that in mind. It might be useful in some questions, it might not be useful, but just useful to know. For those of you that want to know why these central angles are equal, the diagram is going to have to get messy because I'm going to have to assume that this is the prime meridian. Okay, that's not so visible. I'll use yellow. Assume that this is the prime meridian, right? Now, point A1, A2, and A3 lie on the same line of longitude. That means they have the same longitudes. That means the angle from the prime meridian to each of these points must be the same because they had the same longitude. What's the longitude of point A? I had to start from the prime meridian and move to get to point A. The angle formed here must be the same as the angle formed when I move from this primary, the same prime meridian to this same point on the same line of longitude. The angle is the same. So this angle, you can see it, the same as that. Again, because this point lies on the same line of longitude, the angle formed when one moves from the prime meridian along this arc on the same plane to this point A3, this angle here must be the same. So this angle must be the same as this angle and must be the same as this angle. Same thing is true for this angle here, and this angle here. I'm just going to make it clearer. So imagine we have a top view of each of these sectors. So this is the first sector, and this is the second one, which is slightly bigger, and this is the third one. So this is A1, point A1, point A2, point A3, point B1, point B2, point B3, and these points are just the centers of the latitude that these points lie on. Anyway, the key thing here is that the prime meridian, which is essentially this yellow line, essentially can be represented by this line here at the center ish. Now, if one moves from this prime meridian, so I'll just call that P, to this point, an angle is being covered, and that angle is equal to this angle. Same thing here is the prime meridian. An angle is being covered as one moves from P to A2. Same thing here. An angle is being covered, and these angles must be equal. Why? Because these angles represent, for instance, this angle I just shaded represents the longitude of point A1. This angle represents the longitude of point A2 because just the angle formed when one moves from the prime meridian along this arc on the same plane to the point A2. So, and since these lines lie on a line of constant longitude, they lie on the same meridian, then these angles must be the same because these angles represent the longitudes. So, and the same thing is true for this point B1. B1, B2, and B3 lie on the same line of longitude. So the angle formed from the prime meridian to B1 must be the same as the angle formed from prime meridian to B2 and the angle formed from the prime meridian to point B3, which is why I said that this angle must be the same as this angle, same as this angle. So if all the black angles are the same and all the green angles are the same, that means the total angle at the center of this sector is the black plus green. Same thing here, black plus green, black plus green. So that means all these angles are the same. And this demonstrates the idea that points on the same line of longitude have the same longitude. But this is just useful to know. So keep that in mind. So now we want to find the relationship between small r and big R, where big R represents the radius of the Earth and small r represents the radius of a small circle, essentially a line of latitude, the circle formed by a line of latitude. That's not the equator. The equator is the only line of latitude whose radius is equal to the radius of the Earth. The other ones, like the other lines of latitude, like this one, have radii. They're not equal to the radius of the Earth. They're actually less than the radius of the Earth. So r is always less than r. Let's put it that way. Or I can say less than or equal to r, where r is equal to big R when you're considering the equator. So, for instance, this is a line of latitude, and the radius is r from the center to its circumference. Here, from the center, this is the equator. From the center to the circumference, to any point in circumference gives the radius of the Earth. Another thing that has been mentioned is that a line from the center of the Earth, or of this sphere, to any point on that sphere. So call that point P, has a length that's equal to the radius of the Earth. So if I pick any point on the surface of the sphere or on the surface of the Earth, let's call this point A. If I draw a line from the center to that point on the surface, the length of that line is equal to the radius of the Earth, so big R. Where big R, the radius of the Earth, is 6,400 kilometers. Please keep that in mind. So we're trying to find a relationship between big R and small r. I've told you what small r is. If you have let's draw another rough sketch of a sphere, just a line of latitude, that's not the equator. You know, from the top view, all you have is a circle, right? And the radius of this circle is what is small r. If I have the equator here, which is this one here, again the top view is a circle. This is my rough sketch of circle, but the radius is big R, and that's equal to the radius of the Earth, which is approximately, so this should be approximately 6,400 kilometers. So I'm going to find a way of getting a relationship between this small r, the radius of a small circle, and big R, the radius of the Earth. Consider the equator. And consider just another line of latitude. This one just lies to the north of the equator. This is the center of the equator, and this is the center of this circle. That's the line of latitude, this small circle. Of course, the North Pole will be somewhere here, and the South Pole will be somewhere here. And if I draw a line through the sphere, so imagine a three-dimensional object, the sphere. Draw a line through the sphere, through the center of the sphere, to pass through the center of this small circle and the center of the equator. Consider this point A that lies on the surface of the Earth and on this line of latitude. This is the center of the Earth, the center of this equator. This is also a center of this line of latitude, this circle, this small circle. Of course, a line through the North Pole will pass through the center of the Earth and the South Pole, but I won't show that here. Now, the radius of this small circle is small r, so the length of this line is small r. This is center O. I'll call this point B. Now from O to A, we have a line, and if I just locate the point that lies directly below A, will be some point here. I'll call that point C. Now the angle formed between line OA and OC is an angle theta, and that angle is equal to the latitude of point A. If you can't remember why, check the video where latitudes were covered, so the introductory video. This theta here is the latitude. And now if you're looking from this side and you're looking at, let's say you could see through the sphere, what you'd see essentially is this. You see this, but I'll just extend it. So this would be point B. You essentially see the Z shape, right? But since you're looking from this angle, it will look like this. This will be point A. The length of this line is small r. This is point O. This is point C directly below A. And of course, I haven't done something which I left till last. From O through C to the circumference is the radius of the equator, which is equal to big R. So this is O. I'll call this D. So I'll locate D there. So from O to D, it's big R. O to C is going to be the same thing as B to A. But don't worry about that. So this is big R. And of course, remember what I said, from the center of a sphere to any point on the surface, the distance is equal to the radius of the sphere. So if this is the Earth, this will be the radius of the Earth. This angle here is theta. So what I'm going to do is just draw a line, vertical line down from A to C. Remember, C lies directly below A. So all you have is a vertical line, and you have that vertical line being perpendicular to this horizontal line. So I have a right angle triangle. This is R, so this is also R, because AB is the same as OCY, because B lies directly above O, A lies directly above C. So essentially what you can have is a rectangle, to be honest. Splitting it into two gives two right angle triangles. So I'm just going to focus on this one here. This angle here is theta. I'll just write that clearly. Again, this angle theta is the latitude of point A, because the angle formed between the line from the center to point A on the surface and the line from point O to the point C directly below A. Anyway, you must have done a bit of trigonometry by now. If you haven't, check out the trigonometric videos, but there's something called SOHCAHTOA. It's a formula, and from SOHCAHTOA you know that the cosine of an angle is equal to the length of the adjacent side to that angle divided by the hypotenuse of the right angle triangle. So SOHCAHTOA applies to right angle triangles. This is something you must have done in junior secondary. So applying that here, the cosine of theta is equal to the length of the adjacent side, which is this point, this line R, divided by the length of the hypotenuse of the right angle triangle. So this is the right angle triangle we're focusing on. That's the right angle here, as you can see. It's a right angle triangle. So I'll just redraw theta. So cos theta is equal to R over the hypotenuse, the length of the hypotenuse, which is this side right opposite the right angle, which has a length of big R, the radius of the Earth. Now, how did you know, or how did I know, that this side is the adjacent side to the angle theta? Well, this is the angle theta here. The side opposite to the angle theta is this side, AC. The hypotenuse, so this is adjacent, opposite side, or just opposite side. The side opposite to the right angle is always the hypotenuse. Therefore, the remaining side is the adjacent side to the angle. So this is what we have, this relationship. Cos theta is R over R, which if you cross multiply will give you, well, if I write cos theta as cos theta over 1, let's cross multiply. That gives R cos theta, so R times cos theta, or cos theta times R is R cos theta, is equal to R times 1, which is R. So essentially this equation is R is equal to R, big R cos theta, where R is the radius of a certain latitude that's not the equator, and big R, or it doesn't really matter. R, small r, is just the radius of a small circle, a latitude, a line of latitude, and big R is the radius of the Earth. Theta is this angle formed here, and like I said, it's the latitude of the point A we're focusing on. So just focus. This relationship is very useful. I'm going to use it shortly. So if you have to review this video, just review it. But this is a key relationship, and I've showed you how to relate small r to big R using SOHCAHTOA. I formed the right angle triangle and applied SOHCAHTOA and just focus on Ka, which gave me the cosine of an angle is equal to the length of the adjacent side to the angle divided by the hypotenuse of the right angle triangle. We had a point A, and I related the radius of the small circle that point A lies on the boundary of to the radius of the Earth, big R.